Who are online, are you able to hear me and see the screen as well?
Yes, sir.
Just give me a minute. So this was a topic we did yesterday. Any doubts from this topic? Coulomb's law in vector form, right? So we have seen Coulomb's law in scalar form. What does it state? F is equal to K Q1 Q2 divided by R square, where Q1 and Q2 are going to be the charges and R is the distance of separation between them, right? So shall we move on to the next topic today? Next topic of the day. So the next topic that we are going to see is, from the concept of Coulomb's law, we understood that what are the minimum number of charges for you to define Coulomb's law? The minimum number of charges that are required are 2, whereas with respect to the same Coulomb's law, what will happen or how you find the force if it is more than 2 charges? Then you need to go with the concept called as principle of superposition. So as you're able to see, what does this state? So if you need to calculate the electric force experienced by one charge due to the remaining system of charges, then what do? We use this particular principle. So how do we use it? So how do we use it? See, if I take let us say there is a system like this, a charge Q1 and you have another charge Q2 and you have another charge Q3, right? So when you take the Coulomb's law into consideration, you take two charges at a time and the distance of separation between them. Am I right? So if I name this as the first charge, this as the second, and this as the third, so since I'm taking everything to be positive, okay, what will be the force experienced? What will be the force experienced by second due to first? So you call it as F21, right? And which direction is it going to be? When you draw a line, then this is going to be the direction in which it is going to experience. That is F21. Am I right? So if I know the distance of separation between them as R1, now I'll be able to write the Coulomb's law comfortably as F21 is equal to K into Q1 Q2 divided by R1 square. Am I right? Right, this is a simple thing. Similarly, if I have to calculate the force experienced by Q2 due to Q3, then how will I draw? I need to draw a line joining these two charges, and this is going to be what is the correction I need to do? I call it as F23. So F23 will be equal to K into Q2 into Q3 divided by, I'll call this as R2. It is R2 square, right? So if I give a vector symbol on top of it, then what is the unit vector I'm supposed to write? Then what is the unit vector am I supposed to write? It is R21 cap, and this one will become R23 cap. So the net force experienced by the charge Q2 due to the remaining parts of the system is equal to F21 vector plus F23 vector. Am I clear with this? So similarly, if you have n system of n charges present in the system, then you keep on writing. But how should you write them? You should add them vectorially. So now read the statement. So the principle of superposition is used to calculate the electric force experienced by a single charge due to the remaining parts of the system. Then what is going to be the statement for this law? It states that the total force on a given charge is what? It is the, please underline this word, it is the vector sum of whom? Vector sum of the forces exerted on it due to all other charges. Is that clear? Is that clear, guys? So based on this, can we try out a problem? Yeah. Listen. Okay. Now we'll do a problem. There are three charges of values Q, which are placed at the vertices of an equilateral triangle. Okay. They are placed at the vertices of an equilateral triangle. And there is a fourth charge Q dash, which is placed at the centroid of this triangle. So where is it placed? It is placed at the centroid of the triangle. Then what you need to do is calculate the force experienced by Q dash due to the remaining charges in the system. You can keep it. You can keep it there. So due to the remaining parts of the, due to the remaining charges in the system. So how do we do this? So I label this as 1, 2, and 3. Accepted? Right. So if I call this as the fourth charge, what are we trying to do? We are trying to calculate the force experienced by the fourth charge. So the net force experienced by the fourth charge is equal to what? Force from 1. How do we write it? F41. F41 vector plus F42 vector plus F. It's a simple thing, right? Now the question is, if I take the sides of the triangle as A, then what is going to be the distance between the charges 1 and 4, 2 and 4, and 3 and 4? So can I write F41 vector is equal to, how do I write it? K Q into Q divided by, why did I write Q into Q? Actually, it is Q into Q dash. Because the charge at fourth position is q dash, and the charge at the first position is q. And if I take this distance to be r, okay, then what is the value of that r in terms of a? So how do you find it? So if you take the centroid of the triangle, so you will get something like this, right? So this is going to be 30 degrees. This is going to be 30 degrees. Am I right? Why is it so? Because centroid is formed by the point of intersection of medians, whereas with respect to equilateral triangle, medians and angular bisector are the same, right? So if it is going to be 30 degrees here, then if I drop a perpendicular, what is my objective? This distance is r, then this distance is a by 2. So what will be the value of r divided by a by 2? Or a by 2 divided by r? A by 2 divided by r is how much? Sine how much? Sine or cos? Cos. It is cos 30 degrees. So a by 2r is equal to root 3 by 2. 2 and 2 will get cancelled. R is equal to a divided by root 3. Correct? So this is a divided by root 3. So I can write a divided by root 3 the whole square. Am I clear, guys? So why I didn't take r is because in the question only a is given. Okay. Then it is going to be r41 cap. Correct. Is there any doubt? Everyone is clear? Those are online. Any doubt? Clear?
Yes, sir.
Clear. Perfect. Okay. Then what about F42 vector? Even without looking at the diagram, tell me k into q dash divided by a by root 3 the whole square into r42 cap. Then what about F43 vector? K q into q dash divided by a by root 3 the whole square into r43 cap. Right. So according to principle of superposition, what am I supposed to do? Net force vectorially is equal to F41 vector plus F42 vector plus F43 vector. But the only challenge that we have here in this case is the directions are completely different. Am I right? So the directions are completely different. Look at them, no? Because F41 vector, sorry, this is F42 vector. This is what? You already have the diagram in your notes. This is F43 vector. Then what about this thing? F. So aren't they completely different or in different directions? So our job is to solve this problem. So you added them vectorially, but you will not get the answer that easily. So what we can do is we can take the help of resolution of vectors and then solve it. So one thing that I'm clear from all the values is the magnitudes of all the forces are same. Correct? So can I say magnitude of F42 vector is equal to magnitude of F41 vector is equal to magnitude of F43 vector? I'll call this as F. I'm just saying this as F. Then what will happen with respect to the diagram is at point number 4, one force will be like this F, the other force will be like this F, and the other force will be like this F. Okay. Now I'm taking the basic reference coordinate system as X and Y. So when I do this, this F can be resolved, this F and this F can be resolved horizontally. How do you do that? So what is the angle here, guys? What is this total angle? It is 120 degrees. Out of 120, this 90 is gone. Then how much is this angle going to be? Obviously 30 degrees, right? So F can be resolved as F cos 30 and F sin 30, right? Similarly, here this F can be resolved as F cos 30 and this one will be F sin 30. Okay, remember this resolution, it is very important in one of the derivations. Okay, now which components of forces will get cancelled off? F cos 30 and F cos 30 are gone because they are in the opposite direction, exactly of the same magnitude. Correct? So along y direction, what happens? Along y direction, F sin 30 plus F sin 30 they are in the upward direction. So how much is it going to be? It is 2f sine 30 or simply f. 2f into sine 30 is half, guys. So 2 and 2 will get cancelled. It is f. So this direction, the force is f, and downward force is also exactly equal to f. Am I right? So what will happen? So this force and this force will also get cancelled, and answer will be 0. So what will happen to the charge that is placed at the centroid in this scenario? It will not experience any net force. Okay, it will experience force due to the individual objects, but not due to the. Okay. So, but it will not experience a net force. Okay. So now I'll modify the question like this. Instead of q dash, I place q by 4. What will happen? Instead of q dash, I replace, it's the same. Right. So this problem is purely based on the concept of symmetry. Am I clear, guys? So if at all you want to make the charged particle at centroid to experience force, then what are the changes you need to make in the question? Think about it. You change the magnitude of one of the charges. If at all you are able to achieve that, then you can make the charge at the center to experience some force. Is anyone having any doubt? Online students, any doubt?
No.
Clear? Shall I proceed? Yeah. So this is all about the principle of superposition. Okay. The next concept that we are going to discuss is, so we understood what are all the topics that we have gone through. Charge, then we have seen the basic properties of charge, then we saw how to produce charge, right? Then we saw how the charges will interact when two charges are brought, 2 point charges are brought close to each other. Then what did we do next? Then we calculated the force due to multiple charges if you have more than 2 charges. So with this, the concept of charge and force is over. So electric charge, first part is over. Now we need to concentrate on the next part that is called as electric field. Okay. So this is the 8th topic that we are going to discuss. So as the name suggests, what do you mean by electric field? Electric refers to charges here, and field is a region. So electric field basically means if you have a charge and if you are able to define a region around the charge where you try to bring another charge, it will start experiencing force. See, for example, if there is a point charge and there is another point charge that is kept here, if they both are able to interact, then I will state it in a different way. First charge, second charge, and they both are interacting in terms of force, right? If they both are interacting, what I would say is the second charge is placed in the electric field of the first charge. Does it make sense? So the second charge is present in the electric field of the first charge, and the vice versa. The first charge is placed in the electric field of the second charge. So what it will try to do is, see, suppose you have still water, okay? Imagine if you have still water, what will happen if you drop a stone into it? You will have circles kind of thing formed, right? That is basically called as a ripple. So what will happen to the ripple? It will start expanding itself, right? So that ripple will start going and disturbing the other one. You will be able to find only one ripple, or you will be able to find concentric circles. So you're able to find the concentric circles, right? So that is the region in which those ripples are able to interact. So I can, maybe if I have to give a name to it, I'll call it as the region where these ripples are able to interact, or ripple field, if I have to give a name like that. So I'm trying to say that is the area, right? In a similar way, the only thing that is happening is ripples you are able to see, but here you cannot see, rather you can experience. So how you do it? By having some testing device. Okay. So first point, I hope you understood, right? So I want everybody to write down the definition of what is electric field. So because there are two terms we are going to see, one is called as electric field, second is electric field intensity. They both are different, right? So what is it? It is the region around whom. There is a word that is given. It is region around what charge? So why do we call it as source charge? What is source basically? Something which gives rise to whatever we need, right? So here source charge is the one which gives rise to the concept of electric field. Okay. So electric field is basically, electric field is defined for a charge, is defined as what? It is a region around the source charge where you try to place another charge, it experiences force. This is clear, right? Though it is a basic thing, we need to have a different dimension of understanding. Now the question, as I mentioned, you will not be able to see electric field. Then what can happen? Then how are you able to define the concept of electric field? How will you know? If I ask you, is there electric field in this region or not? Find out and tell me. If I give you a task like this, what will you do? The first question that you're supposed to ask me is, whom are you considering as the source? Is it me, this laptop, this water bottle, this iPad? Which is the source? So if you tell me the source, I will take a certain distance from there and try to measure it. Are you able to understand? So first question you need to ask is source. Once you decided the source, you will be able to find the presence of it by or with the help of another charge. So that's what the second point says. The presence of an electric field around a charge cannot be detected unless you bring another charge, because you're not able to see it with your eyes, right? So what happens when you try to bring another charge? It will kind of repel or attract. Okay. So here, how many charges have come into the system? There are two charges. What are they? One is called as the source charge. Then what is the name of the next charge called? You call it as test charge. Why you call it as test charge is because you're testing whether the field is there or not. Are you guys able to understand? So for this point, cannot be detected unless another charge is there. No, the other charge that we are trying to talk about is basically called as test charge. Now comes an important question. When you say there is something called as a test charge, what is the nature of the test charge that I'm supposed to choose so that it is understood universally? So when I talk about a source charge, right, is there going to be any restriction? When I say charge, basically I have two types. What are they? Positive and negative. It is up to me. I can use a positive charge as a source charge or negative charge. It is my wish because I am the one who is creating it. Whereas if I give a test charge, right, let's say you're doing the experiment here and there is some other place or some other school where they are doing the experiment. Aren't we supposed to be on common grounds to understand whether this theory is working or not? So for that, we have to frame something which is universally followed. So for that, what they did is they made the test charge to only be a positive charge. Unless and until it is mentioned anywhere. So you can ask me, sir, can't I use a negative test charge? You can very well use it. But by default, if somebody tells you that I'm using a test charge to detect the presence of electric field, by default, what are they using? Positive charge only is what they are using. Okay. So when a unit positive test charge, that is what they're mentioning here. So when a unit positive test charge, unit is basically 1 unit or a magnitude of 1 value. When a unit positive test charge Q0 is placed near the source charge Q, what will happen? So this is the source charge Q. As soon as you bring the test charge closer to the source charge, what will happen to the test charge? It starts experiencing force. Who will experience force? The test charge will experience force. Now comes an important question. What does Coulomb's law tell us? If two charges are there, each charge will exert an equal and opposite force on the other. Right. So if I have a source charge and the test charge due to the source charge is experiencing force, then will the test charge also be able to exert a force on the source charge? Yes, it will be able to do it. But here one important point that you are supposed to be considerate about is, here you are trying to talk about electric field, right? So electric field is defined for whom? Source or test charge? Electric field is defined only for source charge. So what you need to do is you need to have the magnitude of source charge very high and the magnitude of test charge should be negligible. Only then you cannot make the test charge create an impact on the source charge. This is very, very, very important point. Am I clear with what I mentioned? Is everyone able to understand? Is the logic clear why we are doing it? What should happen? the source charge should have a greater magnitude and the test charge should have a very negligible magnitude. Because test charge objective is what? It will only tell us whether field is there or not. Its work is not to create an impact on the source charge. Are you able to understand? So that should happen. Are we done with the basic concept of electric field? So we understood how to detect the presence of electric field, but we should not stop with it, right? So suppose there is a question like this. Last year you would have learned if I drop this object, why is it falling? You know the logic already. It is because of gravity and you are able to sense. So gravity is present in this region and this is the test charge. This object is the one which is used for testing, right? Now we understood that it is moving. If it is moving, we are also interested. What will be the next step of science, right? You will start finding out what is the value with which it is putting. In a similar way, if at all you have a source charge, then our interest of study is about how much value of electric field is that source charge able to create so that the test charge is impacted. Are you guys able to understand what I'm trying to say? For that, we have the concept called as electric field intensity. So are you able to understand? They both look to be similar, but they're not. What is the difference? Electric field is region, electric field intensity is the mathematical parameter. Right? So electric field intensity and give the mathematical expression for this. So how is electric field at a point measured? Obviously using the parameter called as electric field intensity. Now the question is, if at all I have to give a definition to it, how do I define it? So electric field intensity is always defined at a point. After this, I'll tell you the difference between force and electric field. I'll come to it slowly. But whenever you talk about electric field intensity, right, in the question, they are supposed to mention what is the electric field intensity at a point. Because each point, the value of intensity will keep changing. Okay. So the electric field intensity at a point in the given electric field is what? It is the amount of force that is experienced by whom? By the unit positive test charge kept at that point. First, write down the definition. I'll explain how to interpret. So what is given? It is defined as the amount of force experienced by unit positive charge. Unit positive charge is basically the test charge. Okay. So try to understand. If at all you have a system like this, so how many charges you have? One charge. So whenever you have only one charge, you generally call it as an isolated charge. So what can an isolated charge do? An isolated charge will create a field around itself. Okay. Let's say its field is still here. So what do I mean by its field is still this point? If you go beyond that, okay, imagine there is a boundary. If you go beyond that boundary, you try to place any charge, nothing will happen to it. Means if I have a test charge in my hand Q0, if I place it on the right side of the boundary, there is no impact. As soon as this Q0 enters into the boundary, that is in the region of electric field, it starts experiencing force. Now read the definition carefully. What are they saying? Electric field intensity is defined at a point. Means electric field intensity is created by the source charge, but it is experienced by the test charge. So you're able to understand created, experienced. Okay. So what I'm trying to say here is, when you have only one charge, you talk about electric field. When you have two charges, you talk about electric force. That's what Coulomb's law told us. So whenever two charges come close to each other, what do you speak about? Electric force. Now, can I say that Q naught is inside the electric field? It starts experiencing force. That's what the definition also says, right? So, how will it experience force? Q naught is also positive. I have considered the source charge for the time being to be also positive. So, it experiences a repulsive force along the line joining. Any doubt in this? Right? Let me call this force as F. Okay. This is the Coulomb force that is acting. If I'm able to calculate this force per unit magnitude of whatever test charge that I'm using here, then I can give a name to this value called as E, which is the symbol for electric field intensity. And this is what is called as electric field intensity. Are you able to understand? It's not a derivation, it's basically a definition. That's it. So that is why it is given something like this. Mathematically, E is equal to F divided by Q naught. Q naught is the magnitude of test charge. So you people define the unit for it. It is Newton per Coulomb. Force is measured in Newton, charge is measured in Coulomb. So Newton per Coulomb or Newton Coulomb inverse. There is another unit also which you'll learn in next chapter, but you can write it as of now. It is called volt per meter. You've heard this volt, right? Potential difference. Volt per meter is also called as electric field. Why it is so, we'll discuss it in next chapter. Right. So basically, what is going to be the significance? Now we understood what is electric field and the difference between electric field and electric field intensity. But what does this intensity signify? How is it going to help us? It is going to tell us how strong or weak an electric field is at a given point. So that is the meaning. So the electric field intensity is also referred to as electric field strength, or you simply call it as electric field. Okay, because in problems, what they will do is they'll ask you to calculate the electric field, but indirectly, what are they asking you? It is actually electric field intensity. You should know that. Okay. Now comes an important question. So we learned about electric force, we learned about electric field intensity. These two are the two important mathematical formulas that we have learned till now. Now the question is, are they both interrelated? Means if I know the electric field intensity at a particular point and if I have a test charge, will I be able to calculate what is the force experienced by the test charge? Yes, I can do that with which expression? With the basic definition of electric field intensity itself. Take the Q naught to the other side, then the force experienced by the test charge in a particular electric field is F is equal to Q naught into E. Guys, am I clear? So F is equal to Q naught into E. Shall I proceed? Yeah. The next subtopic that we are going to discuss is, you know what is electric field intensity now. Now our job is to calculate what is the electric field due to a point source charge. Right? What is the electric field due to a point charge? Means I'm trying to say that the source charge is a point charge. Okay. So I have a source charge plus Q. Listen to this, there is very simple derivation. Okay. I have a source charge Q, which is considered to be positive for the time being. For testing the presence of electric field, we have a test charge Q naught. Right. Let's say Q naught is in the presence of electric field due to the source charge. And let's say the distance of separation between the point O, that is the source, and the test charge is R. So the test charge will start experiencing a force in the rightward direction. What is the value of this force experienced according to Coulomb's law? It is 1 divided by 4 pi epsilon naught into magnitude of source charge into magnitude of test charge divided by the square of the distance of separation between them. Right. But what does the definition of electric field intensity tell us? If you know the force that is experienced by the test charge, divide that force with the magnitude of test charge itself. So I will write E is equal to F divided by Q naught, 1 divided by 4 pi epsilon naught, Q into Q naught divided by R square, divided by a Q naught. Q naught and Q naught are gone. So what do you get? Electric field is equal to Q divided by 4 pi epsilon naught R square. Is this formula not similar to something? So is it not similar to Coulomb's law? Except the fact that in Coulomb's law, in the numerator, you will have two charges, whereas in the case of electric field, you will have only one charge. So what is the charge which is there in the numerator? Is it the source or the test? Okay, those are all important points to be noted. So Q divided by 4 pi epsilon naught R square is the mathematical equation for whom? Electric field intensity due to what source, sir? Point source. Online days, am I clear? Kamsini, Harish. Yeah. Harini, are you able to understand? Done. Right. So write down this part. There is a mathematical equation Q divided by 4 pi epsilon naught R square. Now the question is, I forgot to tell this. Is electric field intensity a scalar quantity or a vector quantity? It is a vector quantity. Okay. So why do we call it as a vector quantity? Is because you're writing E is equal to F divided by Q naught. No, this F is actually a vector here. So electric field is also a vector, but Q naught in the denominator is a scalar. So electric field intensity is a vector quantity. So when it is a vector quantity, it is our job to define the direction. Okay, let me see how much you people remember this concept. You guys know what is the direction of magnetic field? What is the direction? South to north. Where is it north to south? So outer it is north to south. Inside it is south. You know this fact, right? So north pole is similar to positive charge in electrostatics. South pole is similar to negative charge in electrostatics. Okay. So if the electric field is away from north pole, okay, in a similar, sorry, magnetic field is away from north, outside, okay, outside. If outside the magnetic field is away from north pole and towards south pole, what do you think will be the direction of electric field? It will be away from. Try to connect the dots. Let me see how we are able to do that. So what did you say? Direction of magnetic field is from north to south. Where, outside or inside? So let's concentrate only on outside. So outside it is from north to south. North is similar to what charge? South is similar to negative. So what will be the direction of electric field? Positive to negative. So there is one important. Don't write it. Don't write it. Okay. Don't write it. Just wanted to try connecting the dots. But I'm not concerned about direction. My question is, who told you that it will act like that? Why did you accept it? Or how did you find it? Magnetic field you have learned in your test. How did you, what test did you do to find out that iron filings? Okay, iron filings, you don't have anything. No, you go and buy something from shop. You have compass. So you're using a compass, right? So compass has what poles? North and south pole. So which pole will you take as a reference to measure the direction of magnetic field? North pole. North pole, what did I say similar to? So their north pole is the test piece. Here, positive test charge is the test piece. You're able to understand they both are actually connected. So trying to connect all these dots, if I have, so I told you yesterday one important point. When you take two charges, right, in Coulomb's law, what is the direction of force experienced by each charge? It will act along the line joining both the charges. Whereas when you have only one charge, that is when you're trying to define electric field intensity, you have only one charge, because one charge is sufficient. That's what the numerator mathematical equation tells me. Okay. how will I define the direction of the electric field due to this charge at a particular point? So direction is always in the direction in which a unit positive test charge will start experiencing force. So let me show this to you. Listen. So I have just a minute. So listen. Guys, are you able to see? One minute. Those are online, you're able to see the screen?
Yes, sir.
Okay. See, I have 1 nanocoulomb charge. Okay. I'm cutting down the direction of electric field. Right. So what is happening here is I have sensors, right? The sensors are the test charges because they are detecting something. So if I place it here, what is happening? So what is the meaning of this diagram? So I have 1 nanocoulomb charge. What is it? It's the source charge. So sensor is the test charge. So in the presence of positive charge, in the presence of positive source charge, in which direction is the sensor experiencing force? Away from it, away from whom? Away from the source charge. Now the question is, will it be the same if I reach now nothing is there? Sensor is experiencing nothing. Now I brought this thing. So look at the arrow mark. The more I bring it closer, the more is the length. What is the meaning of it? More fast it is able to get attracted. So because, oh yeah, one more thing. What did we see in the mathematical equation? Electric field is inversely proportional to R square. So if the distance is decreased, electric field will increase. That's what is happening here, right? So if I place positive and negative, see what is happening. So if I place the sensor here, right? If I place it at different locations, one thing that I'm able to understand is whenever it is closer to the positive charge, the test charge will start experiencing the force away from the positive charge. Whereas when you talk about a negative source charge, it experiences force towards itself. So now read the statement. Now read the statement. What are they trying to tell us? The direction of electric field is along the line joining OP, pointing towards or away? Pointing away from Q. Why is it so? Because Q is positive. Similarly, it will be towards Q if Q is negative. Did you understand why is it so? Because by default, what is test charge? Positive. So positive charge is repel and negative charge is attract. That is a simple logic. Am I clear, guys? So please make a note. If somebody asks you what is the direction of electric field, what will you say? The direction of electric field due to a positive charge is always away from it, and due to a negative charge, it's always towards, because of the logic of repulsion and attraction. I hope it is not tough, right? Shall I proceed? So the same logic again. Now I have only one question to ask before I proceed to this. If at all they have to frame a question, okay, based on charges. So with the knowledge that we have till now, we understood that charges can interact in the form of force and charges can generate electric field around them. If suppose they want to frame a question based on force, what are the minimum number of charges they need to give you? For if there is a question asking you to calculate the force, what is the minimum number of charges there? 2, because what does Coulomb's law tell us? 1 by 4 pi epsilon naught q1 q2 by r square. So the numerator requires two charges. Whereas when they ask a question based on electric field, one charge is enough. So the grammar, the physics language that they use to frame a question is calculate the force between the charges. That is the connecting factor. Whereas when they ask about electric field, calculate the electric field due to a charge at a point. So electric field is always calculated at a point. So if the question is like this, calculate the force at a point. Does it make sense? Force cannot be calculated at a point. Force can only be calculated between two charges. They cannot say calculate the electric field between two charges. Doesn't make sense. They need to say electric field at a point. So this is the language they use. So wherever you see that word at a point, right? Even if the question there are more than two charges and you get confused, this is how you understand a question. Am I clear? Right. Now you see how to calculate the electric field due to whom? Due to a system of charges. We understood how to calculate the forces. There we use principle of superposition. Same logic. Same logic, except the fact that there you have two charges, here you have only one charge. Okay. So if there are number of stationary charges, because electric field is majorly defined when charges are there, if at all you are studying electrostatics, it is better to have stationary charges. So if there are a number of stationary charges, the net electric field intensity, look at the statement, at a point. The net electric field intensity at a point is what? It is a vector sum again, because electric field is a vector point. It is a vector sum of the individual electric fields due to the different charges at that point. So the meaning of this is, let me explain. So if I have a charge Q1, Q2, Q3, and I have an interest of study to calculate the electric field due to all these systems at point P. So what is hidden at point P? What is actually placed at point P? There is a sensor, there is a test charge that is placed. So due to Q1, what is the direction of electric field from the knowledge that we have? Is it away or towards? Away. So can I call this as electric field due to the first charge? So if I place a test charge here, due to Q2, it will tend to get attracted. Along which direction? Along the line joining both. E2. What about Q3, guys? E3. So all the three are vector quantities. So if I have to calculate the net electric field at this point, I will write it as E1 vector plus E2 vector plus E3 vector. One common mistake which people do is, because E2 is like towards the negative charge, they start writing it as minus. Don't do that, because the vector, the arrow on top of it will take care of everything. That is why we say vector sum. We don't say vector difference. Okay. So this is a very, very important point to be noted. Like this, you have n charges, just add the electric field due to all the n charges in which form? Vector form. If you write scalar form, you will never get the answer. Okay. So don't worry, we'll be applying all these things in the next two subtopics. Is it clear, guys? So we understood what is electric field intensity, what is the direction of electric field, and then calculating the electric field due to multiple charges in a system. So then, it is dependent, because it depends on distance r. Electric field intensity is what is electric field? Electric field doesn't have a formula. That's what I told you here. See, did you read the statement? The electric field intensity, read this. The electric field intensity is also referred in the sense, when you talk in a communication language, you can also refer to it as electric field strength, or simply people call it as electric field, because if you open your textbook and see, no, all the problems, they will not say that calculate the electric field intensity. They will only say calculate electric field. You're able to understand. So by their meaning of electric field, they're indirectly asking you what? Electric field intensity. That clarity you need to have. Yeah. Yeah. Distance between what? That you'll know, no? They'll ask you a question. So you try to say that it is independent of the position. Position from where? With respect to the point you're trying to calculate? No, that doesn't make sense. See, for example, if there is a test charge here, Q, if there is a point P here and a point P dash here, are you trying to say the electric field intensity at both the points is same? It is dependent on position. It will be independent of position only if it is lying on a locus. We need two charges. No, we don't need. Because the test charge is Q naught is getting cancelled. That's what the mathematical equation says. You'll not sit and write F by Q. See, try to understand one thing. When they say calculate the electric field intensity due to a source charge at a point, at the point where you're trying to calculate, you are assuming that there is a test charge. You are assuming, okay, we don't know the value of the test charge at all. So what is required is you need to know the magnitude of source charge and the distance of that point charge from the point where you're trying to calculate it. That's it. If you know these two parameters, you can write the formula as Q by 4 pi epsilon naught R square. Is that clear? So it depends on position. That's what I'm trying to say. It depends on position. It depends on the magnitude of the source charge. Clear? Yeah.
R basically means the distance of separation between the source charge and the
Point where you are trying to calculate the field. That's it. Okay. So why I'm stressing on one important point is many of them make mistake with directions. They know the formula, but they make mistake with directions. I've seen in papers. So don't do that. Next time onwards, you know, if it is a positive charge, electric field at that point is away. So draw an arrow mark away from point P. If it is a negative charge, draw it towards. This is the only correction I want you to make. Okay. So having said this, now our job is to calculate a next parameter called as electric lines of force. This is the last topic for the day. Okay. So electric lines of force has another name called as electric field lines. That's it. So you have something called as magnetic field lines. Why I'm trying to connect both is the same thing as the fourth chapter. Fifth chapter and first chapter are the same. Okay. So what am I trying to say? Electric lines of force is also called as, the other name for it is electric field lines. Okay. This concept was first proposed by a scientist named Michael Faraday. Okay. So this has helped them to understand the concept of electric and magnetic field. This Faraday's law, you will learn it in two places. One is electromagnetic induction and the next is in electrochemistry in your chemistry also. So the scientist's name will come up here. Okay. Now we need to give a definition to it. So name is suggesting us something. Electric lines of force. What do I mean by that? So here, one more thing that we start thinking, line means, should it be a line? No. Because we say magnetic field lines are always straight lines. So they're bent also, right? So they can either be a straight line or a curve also. So that's how the definition starts. So electric field, electric line of force, please write it down. Electric line of force is an imaginary straight or curved path along which who will move? The unit positive test charge would move. Clear, guys? Okay, let me explain this. So if you know this concept, right, we need to understand one thing. If you have different kinds of systems of charges, how to draw the electric field lines for them, right? So first thing you are able to see, what is it? isolated positive charge. Similarly, you can have an isolated negative charge. So what is the other combination you can think of? You have a system of both positive charges or both negative charges. And the third combination that is possible is one positive and one negative. Clear? So let's try to do a small test and analyze them. I'm resetting the system. Okay. If I have a positive charge alone, look at the way the electric field is. So what is they trying to say? Now try to connect the definition and see. How are electric field lines drawn? They are imaginary in the first place. Right. In the imaginary part also, if you place a test charge at a particular position, whichever direction the test charge will tend to move, due to whom? Due to the source charge, gives you the direction of electric field. Means if I place a test charge here, look at the red color arrow mark. It tends to move in this direction. If I move it here, you're able to understand. Are the arrow marks in the electric field lines matching with it? So wherever you place, this is what happens. So that is why if you take an isolated positive test charge, the electric field lines are away from it. So this is how you need to draw. So first draw it for an isolated positive charge, the electric field is away. I hope the diagram is helping you, right? You're able to understand. Okay, please draw that. This will be a question that is asked. Similarly, had it been a negative charge, what is the only change you need to do? Yeah, these red color arrow marks you're able to see, no? They would have been towards. So what you need to do is draw a negative charge, draw these kind of lines in the first place, and put an arrow mark in this way. Okay. Now, next, what do we have? We have a system of unlike charges. Okay. So when I have a system of unlike charges, see, this is where the positive charges. I'm bringing a negative charge. Look at the way they are oriented. Are you able to understand? So what is happening here is electric field is always away from positive charge and towards negative charge. Okay, one small difference is you told me when I asked you about magnetic field lines, what did you guys say? Outside it is from north to south, inside it is from south to north, right? But electric field lines do not form a closed loop. They start at positive charge, end with negative charge. Okay, that is infinity, it goes in the other direction. There is no charge nearby. So this is how it works. So you're able to see it, guys, clearly. So why this is there is because you're able to see that it's getting faded out, right? Means they're trying to say that the intensity will decrease as you move away. So this is how actually it looks like. Right? If you want, you can place a sensor and see here it is away. Here it is towards. Right? So this for what kind of system? For a system of unlike charges. Draw this. Because you cannot see them. You can only sense it. You cannot literally draw them on a paper, even if I give you two charges. You can't do it. Maybe magnetic field you can draw. Am I clear? Any doubt? Now listen. So if at all you have a system of like charges, then what? When I say system of like charges, it can be both positive and both negative. So we will reset the system. I will put one positive charge here. Okay. And I'll put an other positive charge. So what is that you're able to understand? Observe this area where I'm placing the cursor. So after this region, you see the electric field lines become parallel to each other. In the sense, they start from positive charge. This is the first positive charge, the left-hand side one. It starts from there. Parallelly, it starts from the second positive charge also. But unfortunately, they can't meet it. Because if you place a test charge there, it will not understand which direction it is supposed to go. So both are repelling. In the previous case, what happened? One was repelling and one was trying to attract. Means one was trying to push it away, one was trying to give a support. But here both are trying to repel. Okay. So that is why if you see, the diagram looks something like this. Here guys, all these questions are asked. So please make a note and ensure you're used to drawing the diagram. Draw it. So one thing is, after you draw the curves, don't forget the arrow marks. Positive charge, put an arrow mark away from it. Negative charge, put it towards it. So here, what is there? Actually, there is a mistake in this diagram. It's a positive. So this is also positive. This is also positive. This is positive. Does it make sense? Right. So this is all about electric field lines. Maybe in the next class, we can start with the properties of electric field lines and some more intense derivations. We'll go to the next concept, that is electric dipole. Then we'll see the derivation maximum. I'm hoping I can complete it by next week, or else 4 more classes. That's it. Okay. So that's it, guys. Any other doubt? Clear? Okay. Revise and come. Start preparing the notes which I told you. Have proper date and all those things. Clear? Metals be charged. Yeah, you can. Charge a metal, okay. You want to charge a magnet, okay. It should be able to, but generally what happens is when you talk, what kind of a magnet are you trying to talk about? Is it a permanent magnet or? A normal magnet is a permanent magnet. So generally when you talk about the permanent magnet, right, it has a different chemical property also associated. So there is something called as domains that are associated. You need to understand the concept of dipoles and domains. Only then I can speak about it. But maybe if you ask the question, I will try and see if it works. So the challenging factor here is I don't know how to charge a magnet. I'm thinking about it. I'll think about it. Please try. They do not form a closed loop. Okay. You want me to reset it? See, you observe it clearly now. Okay. No, look at the arrow marks. No? It starts with a positive charge, ends. Every line is like this. It is not in the opposite direction. Whereas if you see a magnetic field line, they will be in the opposite direction. That is what is called as closed loop. This file will be there in the study materials tab. So there is an option. I think I asked you people to download app. Most of you have not downloaded. Okay. So I know the names, but ensure you're downloading it today. If you have any doubt, reach out to me on the student support number. Okay. All the videos are uploaded and these notes will get uploaded under study material tab. There you can watch it. Okay. Is that all? Oh, perfect. So those who are online, any doubts, guys? Guys, any doubt? Can someone respond, please?
No, sir.
Okay. Okay, then we'll wind up. Please tell me. Name the
Sanjeev.
Sanjeevan. Okay.